So, this course is on light amplification and it is a course on lasers. Okay. So, in this course I will be covering obviously the very fundamentals of the laser principles and also some of the basics of different kinds of lasers that has been invented over the years. And naturally I will be covering or using linear optics, but then I will also introduce to you nonlinear optics, okay, because the study of laser light will be incomplete without nonlinear optics. Okay. And in order to understand the usefulness of lasers and the importance of lasers is by going through the Nobel Prizes that have been won over the years, okay, consistently over the years. So, there have been quite a few Nobel Prizes that have been won over the years. So, the first Nobel Prize that was won was in 1964 and it was given to H. Townes, Nikolai G. Basov and Alexander M. Prokhorov for the fundamental work on quantum electronics leading to the making of masers and laser principles. Now, in this maser, the M stands for microwave, and in lasers the L stands for light, but they are referring to visible light mainly and little bit of the short wavelength maybe in the ultraviolet and a little long wavelength in the infrared. Okay. Now, the next prize came in 1971. These are all Nobel Prizes given in physics and for the topic of lasers. So, in 1971 it went to Denis Gabor for the development of the holographic method. As you can see in that picture there, here in this picture, it's a hologram actually, holographic 3-dimensional one. Here you are seeing it on a 2-dimensional screen, but you can get that feel of the 3-dimensional picturization of it. So, what is done in the holographic method is you have an object, you illuminate it. The next step is the illumination again re-radiates from that object, and this re-radiated radiation interferes with each other, and the next step is to record this interference onto a holographic special holographic plate. Okay. It's like a screen, you know, where this interference pattern is recorded. Then you need another light, a laser light, a coherent light, which has to illuminate this interference pattern, and then you get this 3-dimensional picturization as you can see here. Okay. So, now holographic method has its use in security systems, it has its use in art, in visualization. As you can see, there are so many parameters, you can manipulate all this and get a lovely visualization. Why security? Because it's very difficult to counterfeit holograms. Okay. So, it's not like you take a scan and you get a picture, or you take a photograph and you replicate the original very convincingly. It's very, very difficult to replicate a hologram. Actually, holographic method can be done by a usual light, not a laser light, but it is very, very difficult to get a hologram with that. So, that's why the 1971 prize went to this discovery of the holographic method. Next you come to 1981. Again, the Nobel Prize in Physics goes to the realm of lasers. It was given to Nicola Bloembergen, Arthur Shallow and Kai Sigman for the development of laser spectroscopy. Laser spectroscopy has a versatile use, and it is a very important and useful tool in studying the molecular level occurrences, atomic level occurrences. Okay. So, this spectroscopy method, as you can see in the picture on the right hand side here, It's basically a laser lab with, you can see these lasers are crisscrossing over a table, and the spectroscopic methods are carried out. So there are many spectroscopic methods. One is Raman spectroscopy, one is laser induced breakdown spectroscopy, emission spectroscopy, absorption spectroscopy, and all of them use the laser light. Okay, so without laser these wouldn't have been possible. And in 1981 actually the world was celebrating what should I say, precision spectroscopy itself, may not be exactly laser spectroscopy. Kai Sigban actually got it for electron spectroscopy, okay, very accurate electron spectroscopy, and Bloombergen and Shallow got it for laser spectroscopy. Okay. And in 1997, again you have the Nobel Prize in Physics, which went to Stephen Chu, Claude Cohen-Tanouji, and William D. Phillips for methods to cool and trap atoms with laser light. Who would have thought? With laser, instead of heating up, you are cooling down. Okay. Now, if you see this small, this picture on the right hand side, here in the center, it's actually not an actual picture, it is an imagined one. Animated one, I should say. And so in the center you have a cloud of atoms, and there are 3 lasers which are coming down on it from 3 different directions. Okay. And the basic idea here is you hit the laser and you change and you scatter the laser light. That means the atoms in that cloud are absorbing the laser light and then scattering them back. Okay. So you're deflecting off these photons from the lasers, and in that condition the atoms itself are losing momentum. They lose momentum, they lose kinetic energy, and they finally come down to the lowest level of energy, where the temperature becomes as close to 0 degree Kelvin. Okay, so that's how you cool these atoms. And when you cool these atoms, you come to a state, some exotic state like Bose-Einstein condensate. Okay, and in these states of matter, you can study quantum electronics, quantum optics, and many other. It is an exotic state of matter. It's very difficult to get a matter to cool down to that level and study the physics of it. Okay. Then in 2005, after that, the next prize in the realm of lasers came in 2005. Okay. So this physics Nobel Prize went to Roy S. Glauber, John H. Hall, and Theodore H. Hans for laser-based precision spectroscopy, including optical frequency techniques. So basically it is femtosecond laser frequency comb. That is what they had developed. Now when I say femtosecond, that means 10 to the power minus 10 to the power minus 15 seconds. Okay. So the moment it is 10 to the power minus 15 seconds, that itself is precision. So you can study the occurrences in matter in the time scale of 10 to the power minus 15 seconds. On top of that, what they did is they made a frequency comb. By frequency comb, here if you see in this picture, this in the time scale, these are short femtosecond pulses, very short femtosecond pulses. And in the spectroscopic realm, they are discrete lines with, which are monochromatic and different wavelengths, and they are separated by equal amounts. Okay. They are all well separated by equal amounts, and it is a very stable graph. Okay. So these spectroscopic lines, they look like a comb, you know, one after the other, and they act like a ruler in your atomic and molecular level. Okay. So that's what is precision spectroscopy. Now the next prize in 2018 went to Arthur Ashkin for optical tweezers and their applications to biological system, and also to Gerard Moreau and Donna Strickland for the method of generating high intensity ultrashort optical pulses. These two subjects are slightly different, but of course in 2018 everybody was celebrating the use of lasers and some of the properties that have not been used before. Like Arthur Ashkin was using the property that light produces pressure, and this pressure is proportional to the intensity. Laser light has very high intensity. That's why it can produce pressure that can be felt by these tiny objects. Okay. So what Arthur Ashkin did was he had this say this tiny bead here. This is kind of a schematic diagram, not an actual photograph, but this is a small bead, and this is a laser light, this is another laser light. Okay. Now what you can do with this laser light is you apply pressure, you apply a bit of force, and you are able to manipulate this bead anywhere you like. Here it is a bead, but next to the bead you can see that it's a biological cell or maybe cells together, a tiny object. So Arthur Ashkin was using this laser light like tweezers. You catch hold of them and move them wherever you like, you know. And all this is done without destroying the cells. That was the most important part. This is what Arthur Ashkin did. Now Moreau and Strickland, they were the ones who used the property of light, of laser light, which says that laser light is not exactly monochromatic. It does have a wide bandwidth, and because it has a wide bandwidth, it is possible to get very short pulses, okay, with lasers. And if you see this photograph, it's a very iconic graph. On the X side, these are the years over which the lasers were made, and laser systems, not a single laser but a system of lasers. And on the Y side, you see the power level, peak power level of that laser system. So as you can see, initially it was the power level increased slowly. It had a linear graph like this over this time, and after that, I mean, technologically there was nothing new. So the power level really did not increase much. Now at this point, at the inflection point, that's when Gerard Moreau and Donna Strickland comes into the picture. They invented chopped pulse amplification, a technique which allows you to amplify the power level, the peak power level of any laser system to the petawatt level. Petawatt is 10 to the power 15 watts, imagine that. So with their discovery of chopped pulse amplification, the peak power levels of lasers could go right up to petawatt level, in the range of petawatt level. And people are making such lasers around the world. Okay. And these are used for exotic scientific experiments. Then the latest prize is in 2023, that went to Anne L. Hullier, Pierre Augustini, and Frennek Cross for attosecond spectroscopy and for demonstrating a way to create extremely short pulses of light that can be used to measure rapid processes in which electrons move or change energy. As you can see in the picture on the left hand side, it's a schematic, of course, not an actual photograph of anything. So you see the envelope of the attosecond pulse, okay, here. Attosecond, femtosecond is 10 to the power minus 15 second. So they have used femtosecond pulses to come to a attosecond level pulse. Attosecond is 10 to the power minus 18 seconds. It's such a short pulse. The moment your light pulses become shorter and shorter, you are able to probe occurrences, processes in electrons that move at that rate. And the change in energy of the electrons are happening at that rate. Okay? And unless you have such a short pulse, you are unable to probe such a thing, such occurrences. So that's the importance of the attosecond pulse. So Hulier, Agostini and Cross, they are the ones who invented way of making attosecond pulse and finding ways of measuring it and then using it to study the electrons and its changes in its energy. So that was the last prize in 2023. 24 prize still has to be announced. Now, so that gives you a overview of the laser Nobel Prizes that have been won over the years. They are physics Nobel Prize given for the topic of lasers. Now, what happened is somewhere around 1960 to 1964, when all these lasers were being invented, quite a few lasers came about during that period. Okay? And the first laser that was built was the ruby laser, which is a red light, to be exact 694.3 nanometer. Okay? That was the ruby laser. It is a solid state laser. And yes, so this ruby laser was built by Meeman, a researcher called Meeman, a scientist called Theodore Meeman. And he is the one who coined the term lasers. Okay? And almost immediately after the ruby laser was invented came the helium neon laser, which is again laser light in the reddish region, 633 nanometer. And soon after came the carbon dioxide laser, which is in the infrared region. Carbon dioxide laser was invented by C.K.N. Patel, and it is in the infrared region. 10.6 micrometer or 10.600 nanometer. So it's in the infrared region. Soon after came the argon ion laser, which is 528.7 nanometer wavelength. And so now we have so many different types of lasers, okay, which can be classified into gas laser, solid state laser, liquid laser, semiconductor laser, and fiber laser. Okay. So in gas lasers, you have the helium neon laser, you have the carbon dioxide laser, and you have the argon ion laser. In solid state laser, you have the ruby laser, ND-YAG laser, which is again emitting in the near infrared region, 1060 nanometer. The titanium sapphire laser can be tuned from 670 nanometer to 1100 nanometer. So these three are an example of solid state laser. Then you have the semiconductor laser, or the diode laser you can call it. Here the wavelengths range from 600 nanometer to 160 nanometer. Okay. And then you have the dye laser, which is actually dye dissolved in a kind of liquid. That's why it comes under the category of liquid lasers. And here also you can tune to 320 nanometer to 1500 nanometer. And then you have the fiber laser made of ytterbium doped fiber or erbium doped fiber, and both these, they can be tuned, or you can get lasing action from 10,000 nanometer to 1000 nanometer to 2000 nanometer. Okay. Then you have the excimer laser. Excimer laser, again, it is slightly in the ultraviolet region. As you can see, it has a wavelength of 248 nanometer to 193 nanometer. You can tune it. Basically, it can be tuned to this. Then you have the chemical laser, which goes from 1300 nanometer to 11,000 nanometer. And then you have the free electron laser, which lasers in somewhere around the X-ray region. Now, free electron laser is slightly different from the other laser. During the course, I will be talking about it, and we will know the exact working of the free electron laser too. Now, lasers can be classified into one classification into one more type. So, you can have pulse laser or CW laser. So, what do I mean by CW laser? CW is continuous wave laser. That means you have an output which is continuous. Okay. So, if you see this graph, this is a CW laser, this is a time axis, and this is the output. Now, the laser is continuously giving an output. So, this is a CW laser. Then you have a pulsed laser. Here is the time axis, and here is the output. So, you have this pulse. So, there is one pulse, okay? That is why it is called a pulse laser. But then the pulsed laser, you could have a repetition rate. This is again the time axis. So, you have a whole series of pulses. So, there is a repetition rate, and if the repetition rate becomes larger and larger, it will look more or less like the CW laser. But again, so these are the two types of lasers that you have, CW and pulsed laser. Okay. So, before I delve fully into the laser mechanics, let me give you an introduction to the electromagnetic spectrum. Okay. As this picture shows here, okay, this top picture here, yes. So, this picture shows the wavelengths in the electromagnetic spectrum, okay, ranges from radio waves to microwaves to infrared to visible to ultraviolet to X-rays and to gamma rays. And the picture itself shows that the radio waves have the longest wavelength, and the visible occupies a very small portion of this total spectrum. Okay, the visible spectrum. On the left hand side is a slightly infrared, which is slightly, the wavelength is slightly longer than the visible, and on the right hand side is the ultraviolet, which is slightly shorter than the visible range of electromagnetic radiation. I think, yes, you just have a look at this picture here. This gives you the wavelength. This is the length. It could be in centimeters, nanometers, angstrom, anything. So, this is one wavelength. Okay. So, as you can see in this picture, here the wavelengths are shorter and shorter. So, you have that frequency of those wavelengths is larger and larger. They are all cramped together. So, wavelength and frequency are proportional inversely. You can see here lambda is the wavelength, lambda is equal to c by nu, okay, and nu is equal to 1 upon t, t is the oscillation period. You could give this as the oscillation period, you know, the oscillation period of the wavelength, and lambda of course depends on c and t. Okay. So, this is the electromagnetic spectrum, and this graph actually shows you the electromagnetic spectrum that reaches the earth from the sun. And you can see the visible part of the light, a lot of it reaches the earth. The y-axis gives you the power or the irradiance or the intensity that reaches the earth from the sun. So, you can see the visible light occupies a very large portion of it. Okay. And you can see it all around you, while the infrared light, the right hand portion of it, it's a bit lesser, but you can definitely feel it. You feel it from the sun's rays, and the ultraviolet that reaches the earth is again cut short easily because of the ozone layer, I suppose, and that is short. Okay. But you know, the curve, the dashed line that you can see that is followed, that is called the Planck's formula or the Planck's distribution function, and it is the same as an ideal black body radiation. Okay. So, there is a connection between the sun's rays that reach the earth and the black body radiation.